Yeah, today I'll talk about fine tuning and instruction tuning. So this is kind of the first step in the pipeline of steps that people use to prepare models to be ready to be used as chatbots, like what you see in ChatGPT or Gemini or whatever else you want to be using. And what this basically takes advantage of is that we have many, many different tasks that we can be solving in NLP. And each requires different varieties of data. So up until this point, we've talked a lot about the varieties of tasks that only require text, such as language modeling. And then we also have other varieties of tasks that require only naturally occurring data. So like data that we don't actually have to create by hand, or that we don't have to create by hand for the purpose of training like language models or NLP models. And this includes stuff like machine translation. And the reason why we have lots of machine translation data is people do translation anyway. Even if we didn't have like ChatGPT or Google Translate or something, people would be doing translation. And a lot of this data can be used to train models. Then other things are hand-labeled data. And so this is like, for a lot of things like question answering or other tasks that you need to create data like named entity recognition or stuff like this, that data really mostly isn't naturally occurring. So we need to go in and actually create it by hand in order to do training. So like one of the interesting things about, the whole paradigm of training language models over the past several years is that we have been remarkably successful in getting models to work at a very large number of tasks by training only on text. So, we trained something like Llama, or we trained something like the early GPT models that were trained only on text without very much supervised training data. And the reason why is like what I mentioned last class, which is like actually a lot of data on the internet just occurs in this form anyway. So we have things like phrase books that appear online. And these phrase books weren't explicitly created as machine translation data or translation data even, but they appear online. And there's actually a paper that examines this. That I didn't cite in the slides, but it's a kind of interesting paper from ACL this year, where they find that despite the fact that there's a language model that was trained on just random data from the web, they found over 30 million translation pairs across at least 44 languages in this data that was just like scraped from the web, not explicitly for translation. And so there's lots of other examples of this, question answer pairs from FAQ pages on sites or other things like that. So, but anyway, yeah, getting back to the original thing here, in many cases, your models will have already been exposed to some data. There's some naturally occurring data that you can harvest and curate in an appropriate way. And then sometimes if you really want models to do something well, you can do handwriting, but that's very expensive and you're not going to be able to create very much data. So one very funny thing is I was playing around with GPT for translation, and I asked it to translate from English to Japanese. And it did really well most of the time. It did, very good translations on English to Japanese in like 900 out of the 1,000 examples. Sometimes it just got it wrong because it's not a perfect translation system. But every once in a while, it would translate into Japanese, which is in Japanese characters. And then it would translate into Romanized Japanese, into like the pronunciation. So no Japanese translator that you asked to translate into Japanese would ever do that. That would be like extremely unprofessional, right? You're saying, please translate this into Japanese for Japanese speakers. But why would GPT do this? Anyone have any ideas? Yeah.
Someone on the internet did it that way, or something?
Yeah, someone on the internet did it that way. So a lot of the times when you have incidental training data on the internet, it would be from like phrase books of people who are trying to teach Japanese, for example. So every once in a while, like GPT got the idea that it should be translating like it did in a phrase book for Japanese learners as opposed to, like actually English to Japanese translation. So the problem is if you're learning only on this language modeling based text, you might get exactly what you want, but every once in a while you'll get something completely crazy that you never expected to happen. So that's the problem with just relying on base language models when we're doing training. So all the methods that I'm going to be talking about here fall in under the class of multitask learning. And so multitask learning is training models to do well on multiple tasks at once. Just to give an example, you could have this as an example, and you could be doing language modeling on it. You could also be training a model to do tagging on it and other things like this. And exactly how you do this can be different. But the important thing is that you have some shared parameters between the models that are trained on all tasks. And if you're just training a big language model, then you'll probably be sharing all of the parameters. If you're training something like BERT, or like you're pre-training and then fine-tuning, you might train the body of the model on multiple tasks, but have a separate classification for different tasks. So there's different ways you can do that, but the basic idea is that you need to have lots of shared parameters. One easy way to do this, the very simplest way to do this is to train the model and sample one mini batch for one task, another mini batch for another task, and just alternate between them, or alternate between them and sample 4 from one task and 1 from another task. So it's often as simple as that. Or you can just, or you can just mix all of the data together. So if you're doing like text, everything is text-based, then you don't even need to worry about mini batches. Cool. So separately from this, pre-train and fine-tune. So in pre-train and fine-tune, you first train on one task and then on another. And the way this works is you first train, for example, a language modeling objective. And then after you're done training the language modeling objective, you train on something else like tagging. And there's several reasons why you might want to do this. Does anyone have an idea about why you might want to do this? As opposed to something like standard multitask learning where you do both of them at the same time? This is a straightforward question, perhaps, but when I say straightforward, I don't mean easy. I mean not a trick question. Any ideas? Okay, how many of you have trained a 70 billion parameter language model from scratch? I see somebody say maybe, so that's actually pretty impressive, but why not? Yeah. Yeah, it's unbelievably expensive and a waste of resources. Yeah. So like if everybody was doing it, it would be a waste of resources. So we actually benefit a lot by a very small number of people doing this pre-training, and then the rest of us doing, fine-tuning on a smaller amount of data. So if you were doing all the multitasking from scratch, then that could be a waste. Does anyone have an idea why you might not want to do this? Or actually, there's some other reasons why you might want to do this. Another reason why you might want to do this is, for example, if your pre-training data is big and messy, like for example, if your pre-training data is all of the internet and the internet contains like lots of toxic text and text that's in a format that you don't want, you can still train on it and learn from it. But then fine-tuning can, make your model safer or remove toxicity or other stuff like that as well. So does anyone have an idea why you might not want to do this? This is a trickier question. Any ideas? Or to put it in a different way, why you might want to do standard multitasking instead of this? Yeah.
Just again, so if you don't have much checking data, for example, then you might consider like doing more
Uh, so if you have lots of tagging data, I think yeah. So I think you're basically, this is a good point. So if you don't have lots of tagging data, you might have much more language modeling data than you have tagging data. So it's a better idea to train more on it. That is true, but you could sample like 99 mini batches of language modeling data in one mini batch of training data, or 999 of language modeling data. So it, it's a good, going in a good direction. Anything else? Yeah.
Pre-training data with certain biases you might inherit.
So if your pre-training data has certain biases, you might inherit it. Do you think that's a bigger problem with pre-training or pre-training and fine-tuning or standard multitasking? Yeah.
I think the reason why you might not want to do this is perhaps you could lose some of the representation that exists between the multi-class data sets.
So you might lose some of the information that exists in the multi-class data set. I think that's pretty close to what I'm going to say. So let me just go ahead and give the answer. Hopefully everybody had time to think about it. But this is a paper that we wrote previously, and basically one interesting thing is that you actually do better. You do better if you train on multiple tasks at the same time. And our hypothesis about why the reason you do better on the end task that you finally want to do well on compared to pre-training and fine-tuning. And our hypothesis about this, which I've also seen a few other works, is if you pre-train on the task that you finally want to solve, while you're also solving the language modeling task, the essentially the model is learning representations that are useful for both at the same time, as opposed to if you're training on the language modeling task, it will be learning representations that are useful for the language modeling task, but not necessarily focusing on the representations that would be useful for the end task. So like, for example, if you're jointly training on sentiment analysis and language modeling, the representations that are useful for sentiment analysis will be more salient in the model, essentially. And so that will be particularly a problem when there's multiple, when you have a varied optimization landscape and multiple local optima, and the language modeling might not get you into the global optimum that you want for the end task that you're solving. There's also another interesting paper from Anthropic more recently than ours that shows something a little bit similar, specifically from the point of view of safety training. And they demonstrate that if you start out by having a concept of safety early in your training, you're able to reach better final results than if you start safety training after you've trained your model for a while. So, and this is particularly for things like toxicity. So there are downsides to pre-training and fine-tuning, but the upsides of spending lots of compute once and then fine-tuning for lots of different downstream tasks is like large enough that that's still the standard nowadays. Any questions about that? Okay, cool. Let's move on. So we talked about prompting before. I'm just going to go over that very quick. Just say it for completeness. But when we're prompting, we have an encoder. We train it on language modeling or whatever else, but then we freeze it and then we specify the task by a prefix like this. And what instruction tuning does is instruction tuning is like a combination of fine tuning and prompting. And so what we do is we pre-train and then oh, sorry, I guess I failed to update the figure here. So this is just the figure for fine tuning. So normally what you do is you have a prompt for one task, a prompt for another task, a prompt for another task. And then you train your model specifically so that it does good completions of those prompts. So it'll give some actual examples of that later. So yeah, sorry, the figure, I will need to fix that. Just taking a note. Um, okay, so we haven't really covered fine tuning yet in general. So I want to talk a little bit about what we do for fine tuning, and particularly what we do for fine tuning very large models, because I think that's what a lot of people want to do nowadays. So for um, full fine tuning is relatively easy. What we do, easy conceptually, hard in practice. So what we do is we simply continue training the language model on whatever data we want to be fitting to. So this could be like translation pairs, it could be question answering pairs, it could be anything else like that. But the issue is, depending on the method that you're using to optimize your model, the method can take lots of memory, and also in some cases it can be relatively unstable compared to some other alternatives that I'm going to talk about in a bit. And just to give an example, training a 65 billion parameter model, which is the largest version of Llama 1, with 16-bit mixed precision actually takes much more memory than you would expect if you haven't done this before. So if you look at the amount of memory required for holding the model in the first place, if we have 65 billion parameters times 2, that would be 130 gigabytes of memory already. So that's already a lot of memory, right? But if we want to do, if we want to hold both the parameters and the gradients of the model, obviously we need to double the number of points here. So we also have 130 gigabytes for the parameters. Sorry, for the gradients. Then we have the optimizer, and this could be an optimizer like Atom. If people remember, Atom has first moments and second moments, so it has the mean and something that looks like the variance. And these, at least according to this paper from 2019, needed to be stored in 32 bits. So these needed to be stored in 32 bits of memory, because if you store them in smaller amounts of memory, they would have underflow issues, overflow issues, and basically the numerical precision would destabilize your training. And then in addition, the parameters also needed to be measured in 32 bits. So you needed a 32-bit copy of the parameters. This is just the parameters of the model. And then separately from that, you also need to do the forward and backward passes. And so if you do the forward and backward passes, depending on how big your batch size is, how many tokens you have in each instance, this could take, significant amounts of memory too, like 100 to 200 gigabytes. So overall, this would take around 1,000 to 1,400 gigabytes of GPU memory in the very naive scenario. And this is not that great. Now, this paper was written in 2019, and there have been some advances since then in optimizing models. So to give some examples of things that can be fixed, previously, when we were using FP16, so like the regular ANSI floating point numbers like we use on our CPU, this was it. You needed 32-bit integer, 32-bit floats to make this stable. Now it's pretty standard to use BF16, brain float 16, like I talked about earlier in the class. And because of that, this can be made more stable, so you can reduce this to things like 2 bytes instead of 4 bytes. We can also, if we do that, we don't need this extra copy of the parameters. So we can get away with about 8 bytes per parameter we want to optimize, but that's still, a lot of memory. That's 130 gigabytes of memory for a 65 gigabyte model. And the forward and backward passes still take space as well. So basically what I want to say is full fine tuning is pretty memory intensive. And if we look at how big a standard GPU is, I took some specs here. The memory is just the memory on the GPU. The cost, I did a very unscientific thing of Google the price on Amazon and take a look at the price of the GPU here. And then on the right side, this is the types of cloud machines that support these GPUs. And in this class, a lot of people are using Google Colab, I think, for your current assignment, and soon we'll have AWS credits for everybody, so you can use AWS machines. So if you look at the GPUs that are available, we have things everywhere from 24 gigabytes, 32 gigabytes, 40 to 80 gigabytes, 48 gigabytes, or on your Mac, the GPU and CPU memory is shared. And basically, what we can see is that there's no GPU with 130 gigabytes of memory, right? So none of them can do this with a single GPU. There's also a bunch of other hardware options like AMD GPUs, Google GPUs, special purpose training things like Cerebras, AWS Trainium, et cetera. But I think for the purpose of this class, you're probably going to use standard hardware like this. So anyway, like that model will not fit on any, or that fine tuning will not fit on any GPU that you have available to. Any questions about this? Yeah.
What are the other like special purpose hardware used for?
So a lot of these are created specifically for training neural networks. So they're like really, really good at the things you need to be training neural networks for. I haven't actually used any of these, so I can't like endorse or disendorse any of them, but they're made to be like really good at training transformer language models or like the specific thing that everybody wants to train. The disadvantage is if you start wanting to be like a little bit more creative than what they imagined, it might not support that. So that's also a problem with TPUs. TPUs are very good at certain things, like they're very good at like batched large operations, but they're less good at nimbly executing dynamic computation graphs and stuff. So from that point of view, I think most people in research still use GPUs. One thing I should mention is the AMD GPUs. A lot of people have started using them in like 2023, 2024. Like I think previously it was kind of a NVIDIA one horse race, but I've heard more and more people using AMDs, so. And they're not price gouged quite as much. So. Any other questions? So training models, like if they're pre-training models, they're using like 1,000, 1,000, 2,000, 4,000 or something. Like they, Meta just announced that they got 350,000 H100s or something like this. And in case you are too lazy to calculate, that's about 10 to $20 billion. It's a lot of money. And I'm sure not all of them are being used to train a model. A lot of them are used for model surveying and stuff like that. So, but there's a reason why we're not all pre-training models, right? It's a big effort. It's very expensive. So. Cool. Any other questions? Cool. Okay. So how can we overcome this? The first way we can overcome this is using things like multi-GPU training. And one solution is just to throw more hardware at the models and distribute the models over multiple places. And the canonical or the most well-known version of this that still many, many people use when they're pre-training or fine-tuning language models is something called Deep Speed Zero. And the way Deep Speed Zero works is it works by partitioning optimization over different devices. And so there's different stages of deep speed. The first one is this one right here. And this says 2 plus 2 plus k, where k is the size of the optimizer state that I had here. So 2 bytes plus all of the bytes required for this. And the blue is the first two, the orange is the second two, and the green is the third one. And so basically the baseline is you hold all of these on each GPU. the second thing is you partition the optimizer state across different GPUs. And because optimizer state is generally larger or at least as large as all of the others, this can reduce memory requirements significantly. So this went from 120 gigabytes for whatever model they were doing there to 31 gigabytes based on, so this was a 7.5 billion parameter model. So and they had, let's see, yeah, and they had 64 devices. So they went down from 120 to 31. This is with 12 bytes for their optimizer state, like I said here. But actually, we can get away with 4 bytes for the optimizer state. So actually, you can train a 7 billion model reasonably easily on, 1 or 2 devices, one or several devices now with this. So this is called stage 1. This is partitioning the optimizer state. Stage 2, this is partitioning the optimizer state and the gradients. The optimizer state is actually, doing the optimizer state is actually relatively like harmless. It doesn't slow down too much. Partitioning the gradients gets a little bit more tricky because you start having to move things between devices a lot. And then if you do this for the parameters, you can do even more. So you can get it down to like ridiculously small values here, but this is going to be very expensive in terms of moving things around so that you can calculate your gradients appropriately. So I'd say that by default, if you can go to deep speed with like stage 1 or stage 2, you can spread this up across different devices and trade models. Yeah.
It's just a general question that multi-GPU training, does your central device that is doing like the allocation? I think that does it need to have at least
does your central device, can basically be your CPU. When you say multi-device, sorry, do you mean multi-GPU or do you mean multi?
Like,
okay.
So if they're, let's say on the top, your CPU needs to be, like, it needs to be able to handle that.
I don't think so. I mean, it depends on the implementation, but not theoretically anyway. And I can deep speed handles that for you. Yeah, otherwise you'd have lots of trouble like getting the machine that had 1,000 gigabytes of memory. So yeah, I would suggest definitely using something like deep speed, but actually a lot of libraries use deep speed under the hood also. So things like Hugging Face Accelerate, GPT-NeoX, other things like this, they all interface. Many of them interface to deep speed or something similar to it. So whatever library you're using for training like this, you can do. I don't have a list, but there's a whole bunch of them. You can either use deep speed, things like Hugging Face Accelerate or TRL. I think we might have a TRL recitation later. Also, I haven't used it myself or worked with people who've used it, but Axolotl, a lot of people are using. So maybe we could come up with a list of those later. So the other option that you can use is don't tune all of the parameters of the model, but just some of them. And this is really popular nowadays because this further improves your ability to train on many different, data sets without huge GPUs or without many GPU devices. And so the first one is something like prefix tuning. So I already talked about this last time. Prefix tuning is like a bridge between parameter efficient fine tuning and prompting, right? So it tunes one prefix for each of the layers. So the next one that I'd like to talk about is adapters. And adapters basically look like this. So what you do is you have your standard transformer architecture, which has, like multi-headed attention and other things like this. And yeah, this is written in a slightly different way than I wrote the transformer diagram, but it's saying the same thing. So multi-headed attention, this is kind of your your Q, K, and V matrices. And then this is your O matrix um, in the transformer architecture. So this is what we were calling multi-head attention in the previous diagram. This says 2x feed-forward layer. It's basically 2x linear layer with a sandwiched nonlinearity. So it's basically a feed-forward block. So this is just the standard like transformer. So what adapters do is they add yet another layer right here. And you freeze the things that are in gray here, like the feed-forward layer, multi-headed attention, but only train this adapter. And the way the adapter works is you have a standard large representation vector here, and you have a feed-forward down projection that down projects to a very small number of nodes here. And then you have a nonlinearity, and then you have a feed-forward up projection that projects it back to the standard space. And this is included within the residual layer here. And so ideally, this will project down from like 512 to something like 16. And then back up to 512. So if it was just a 512 by 512 matrix, that would be 2 to the 9, right? So you get 2 to the 10 parameters. Right. Not 2 to the 10. 2 to the 18, right? Yeah, 2 to the 18 parameters. This is only 2 to the 4. So if you have this, that would be 2 to the 9 plus 4 plus 1 is 2 to the 4. So you would have 16 times less parameters for the adapters than you would have for the full matrix. So, and then if we, instead of using 16, we just did 2 or 1 or something like that, it would be, much, much less. So basically, by making these matrices or these vectors very, very skinny, this allows us to minimize the additional parameters. So are there any questions about this? Yeah. Yeah, so why do they make it smaller and then larger? The main reason why they make it smaller and then larger is because that's a way to reduce the parameter count. So if they kept it the same size, it would be 2 to the 18, but you would actually have 2 of them. You would have 2 of them, so you'd have even more parameters. But so it would hurt the performance. So making them smaller would hurt the performance if you had lots and lots of training data. So if you have lots and lots of training data, you would benefit by making the adapter dimension larger and just fitting very well. But if you have lots and lots of training data and you have the memory that allows you to train a larger model, then you might as well just train the whole model itself. You might as well do full fine tuning. There's 2 advantages to parameter efficient fine tuning methods. The first one is that they reduce memory, like I mentioned here, reduce the memory for the parameters you're training. Also, because there's fewer parameters, it's harder to overfit. So if you have very small training data, full fine tuning can overfit and become unstable. But because this has fewer parameters, it essentially is less easy to overfit and will generalize better often. Yeah. So when you fine tune, you only fine tune the parameters of the adapters. And so we assume that we have a pre-trained model, like the gray parts are pre-trained, and then we fine tune just that. Yeah.
We're updating vector layer, but we couldn't do the gradient other layers in the vectors.
So very good question. You need to So the question was, even though we are only fine-tuning the adapter layers, we still need to store the gradients of the other layers, right? So we still need to store this part. That's actually not the case. So when you are doing backprop, you only need to do backprop into the parts of the model that are on the path to the gradients that you want to be updating. So like, for example, if I write the computation graph, so this is like the computation graph of a an attention block. So we get our loss, like the gradient from the loss is flowing in here. And so it goes back to the feed forward network, to the adapter, to the attention, and then here. So we definitely need to pass it back through the layers so we get to, you know, like the earlier layers and stuff. We don't actually need to pass it into this, into the weights of the attention, because we're not updating them, so we don't really need to even calculate the gradients of the weights of the attention. We also don't need to calculate the gradient of this. But we do need to calculate the gradient of this because we're updating it. So basically, you don't even need to do backprop into parts that you can just cut off without updating. Yeah. For forward, you do need to, you know, use them obviously to calculate the forward pass. So by like being smart about that, you can fix that. There's also something called checkpointing, like computation graph checkpointing or forward pass or backward pass checkpointing, where basically what you do is you calculate part of the way through the graph and then throw out the intermediate calculation. And so, for example, you might do the forward pass all the way up to here, and then throw out all the intermediate states, and then recalculate them when you're doing the backward pass. And so there's like lots of tricky things that you can do to like squeeze your memory if you need to. Yeah. Great question. Do I have that on the slide? Maybe not. So one way that you can do it, this is from LoRa, but the same idea is basically there. So in LoRa, you do the upscaling with a zero matrix. You initialize it to a zero matrix, and the downscaling, you can initialize it to zero or like some random. No, actually, this needs to be random. And so the reason why this is zero is because then if you don't do anything, it will just stay the same, right? So, so that is the standard way of initializing. Cool. Okay. So another thing that I want to mention, this is a kind of interesting technique. It's not super standard, but I like it. So I'm going to talk about it anyway. This is something called adapter fusion. And the basic idea is to learn an adapter for various tasks and combine them together. And so instead of having just your adapter layer, you have multiple adapters, and then you have adapter fusion up here. And the basic idea is an adapter is just, you know, what I wrote on the previous slide, but adapter fusion is attention over adapters. So you can decide which adapter to use in which case. And each of the adapters is trained separately on like task specific data. So you have data from lots of question answering data sets, and you train a question answering adapter. You have data from I don't know, translation data sets, and you train a translation adapter, you have other things like that. And so then when you actually use them, you do attention over which adapter to use and then take the value from that adapter. And I kind of like this idea because it allows you to, train modules that are useful for a particular task and then decide which one to use at any particular point. So I think there's lots of creative things that we could do with this. There's also multilingual versions. So you train adapters for individual languages and you train adapters for individual tasks, and then you combine them together too. So if that's interesting, you can take a look at that on paper. In a way, this is kind of like a mixture of experts model, if you've heard of that. We're going to talk about that in a future class, so I won't go into lots of detail, but I wanted to talk about it here while we're talking about adapters. Cool. Okay, so now I want to go into talking about LoRa. And LoRa is very popular. It's very likely that you've heard of it nowadays. The way LoRa works is very similar conceptually to adapters, but it has an important implementation difference. And the difference is that in contrast to adapters, which had a nonlinear layer here, LoRa has no nonlinear layer. So basically what it is doing is it is taking a downscaled matrix, an upscaled, downscale matrix, an upscale matrix, and just doing a linear transform with them. And so in this graph, or in this figure here, which I took from the LoRa paper, it's actually showing them as like separate computation paths. It's showing like you use a normal matrix and then you use the LoRa matrix separately. But actually, you can just add them together and you get the equivalent result. So you add this matrix times this matrix into the pre-trained weights, and that gives you the same result as if you calculated them separately and then added them afterwards. So why is LoRa so popular? I would say LoRa is so popular because it's super convenient after you finished training with LoRa. Because after you finish training with LoRa, you can just add the learned matrices back into the original weight matrix, and you have a model that's exactly the same shape. It doesn't have any other components. You don't need any different code path. You just have updated parameters. And that contrasts to adapters, because in adapters, you actually need to add extra model components. You have to have different PyTorch code to implement this. So I think that's the big reason why LoRa is so popular here. It's not actually that complicated. It's pretty simple, but it's important to know. Cool. So another popular thing that you might have heard of is QLoRa. And QLoRa combines together quantization with parameter efficient tuning. And we're going to talk a lot more about quantization in a future class in maybe a week or so. But basically, there are ways to compress the model down to not be in like 16 bits, but be in like 4 bits. And so if each parameter is in 4 bits, that makes the model very, very compact. And so if we go back to our calculation in this previous slide, if we had a 16-bit model to fit Llama on your memory, you needed 130 gigabytes. But like, let's say we have a 4-bit model, suddenly it's not 130, it's something closer to 32 and a half, I guess. And 32 and a half actually fits on a lot of hardware. It fits on A100s or H100s easily. It also fits on these like less expensive GPUs. I mean, less expensive might be, relative, it's still very expensive, but it'll also fit on your Mac, probably, if you have a Mac with a fair amount of memory. So you could just run it on a local machine in your CPU memory also. So basically, the idea is we can press down the model to be much smaller, so the forward and backward, so the parameters are small. And then we have a very, very compact LoRa layer that doesn't, LoRa, which doesn't take very much memory itself. And that allows us to basically train a model on, commodity hardware, like 48 gigabyte GPU, or something like your MacBook or something like that. And it also has like paging to page things from CPU to GPU memory to make it even more efficient. But basically, that's the general idea. So I definitely, if you want to train a large model on limited hardware, I'd recommend this. If you're not training a super large model like 65 gigabytes, I think just LoRa should be fine. Like you can probably train a 7B model or a 13B model with just LoRa, and that should be on a single GPU. Cool. Any questions about this? Does low precision not cause any problems? It definitely is. You need to be a little bit concerned about it, but you're not doing optimization in low precision. You're just keeping the original model in low precision. So from that point of view, it's, it's manageable, I guess. So. And you can also look at the Hugh Laura paper. They have very extensive experiments. Cool. A final one that I'd like to talk about is BitFit. This is very, very simple. You basically just train the biases of the model for any model that has biases. This also can fit models. It's very simple because you don't even need to chain. You don't need to add any extra code. You just need to freeze all the parameters except the biases. So from that point of view, it's very easy. So I talked about this a little bit last time, but I think everybody didn't have full understanding of all the parameter efficient tuning methods to understand this well. But we had a paper where we basically looked at all of these tuning methods and we kind of decomposed them into several different design components. And actually, maybe I'll also pull up the table that we have of this. That might be even easier to follow. So basically, there's different things that you can look at with respect to parameter efficient tuning methods. There's the functional form of the nonlinearity that you're using. There's the place where you insert the model. There's how you modify the representation, and then there's a composition function for how you take the modified representation and add it into the original representation. So if you want to take a look at the table, you can take a look at this. It's also in the references. But basically what we can find is that things like adapters, LoRa, and prefix tuning are actually very similar to each other. With the difference being, where do you get the original representation that you're feeding in? So adapters generally get it from after the module that you're adapting. Prefix tuning gets it from before. LoRa also gets it from before. Also, what's a nonlinearity? It's a ReLU, a softmax, or nothing. LoRa actually, this isn't really mentioned in the paper, but it is like actually implemented in the code. There's also a scalar scaling factor here, which is a hyperparameter. So that's something to be aware of. And so basically by breaking these down, you can, number one, better understand each of the modules and how they, or each of the methods and how they interact with each other. And also what we show in this paper is that this understanding can lead you to, new variants that can be more effective than any of the existing variants. And so we propose two things called the parallel adapter and the scaled parallel adapter, and we demonstrate that they get better results. So then the question is which one to choose. For convenience, LoRa and BitFit don't change the model architecture. So if you don't really care about like the absolute best accuracy out of these tuning methods, I would definitely recommend you use something like this. It's definitely the easiest thing after you're done training. For accuracy, one thing that we found in our paper, for simpler tasks, it really actually doesn't matter very much. So if you're just doing classification tasks, even something super simple like BitFit is rather competitive with all of the other methods. For more complex tasks and a small parameter budget, we found prefix tuning to do a pretty good job. This is not a like universal finding, but it's what we found in our paper. And then for more complex tasks plus larger parameter budgets, adapters or some sort of mixture of multiple methods can give you better results. So again, all of this is in the paper if you want to look at more details. Cool. Okay. So any questions about that or? Okay. Next, I'm going to go through some NLP tasks. And the reason why I'm going to go through some NLP tasks is because when we're fine-tuning, we need to be fine-tuning towards individual tasks we want to solve. And so basic fine-tuning, we build a model that's good at performing a single task. Instruction tuning, we build a generalist model that is good at many tasks. And what I want to go through now is I want to go through some tasks that I've seen people use. Number one, being really important in like actual applications of NLP models in industry. But number two, what is the set of tasks that people use to evaluate generalist models? So like if you look at the GPT papers or you look at the Gemini paper, what is the set of tasks that they're using to demonstrate that their models work well? So the first one is context-free question answering, also called open book QA. Basically, this requires answering a question without any specific grounding into documents. It's also what happens when ChatGPT answers your questions without looking something up on the web, for example. An example data set that lots of people use is something called MMLU. This is a massively multitask language understanding data set, and it has questions in a number of relatively difficult areas like professional law. So this is asking what happens when a salesman ignores a trespassers will be prosecuted sign and enters a hermit's house. He drives up the driveway and an explosive charge explodes. The seller was injured. Can the seller recover damages from the hermit? So I would not be able to answer this with certainty because I'm not a lawyer. The answer is yes, if the hermit was responsible for the explosive charge under the driveway. So now you know you can collect damages if somebody tries to blow you up when you trespass on their property. But yeah, and this has lots and lots of categories like this. The next thing is contextual question answering, and this is question answering grounded in actual context. One example data set that a lot of people use is something called natural questions. And this is questions grounded in a Wikipedia document or the Wikipedia document collection. So grounded in a Wikipedia document means they give you the actual document you should be answering the question about, and then you need to answer the question about it. This is often called machine reading because you expect it to like read and answer questions about the document. Or it could be, okay, we're going to give you all of Wikipedia. Please provide us the answer to this question. And this is often called retrieval-based question answering or retrieval augmented, one variety of retrieval augmented generation or RAG. So this is really, really important. I think many people that I talk to who want to build actual systems from language models or NLP systems are trying to do this sort of thing. The second most popular thing that I talk to people who are trying to build like NLP systems of some variety is code generation. And basically this is simply generating code like Python SQL from a natural language command. The most popular data set for this is something called HumanEval. And basically it has questions about the Python standard, how you do things with the Python standard library, like return a list with elements incremented by 1. It gives you the text and several examples of what the inputs and outputs should be, and you're supposed to return a program like this. And this is a simpler version of this. There's also more complex ones. One thing I should note, this is an area that I do a lot of research in. HumanEval is a very simple example of this. It doesn't use any external libraries. It doesn't use context and other stuff like that. There's a lot of other more interesting data sets also. So if you're working on code generation, I can recommend those as well, and I'll do that later in the class too. Cool. Next is summarization. And summarization, there's a couple of varieties of this. One is single document summarization, another is multi-document summarization. A single document compresses a longer document to a shorter one. Multi-document compresses multiple documents into one. Honestly, right now, single document summarization in English works pretty well out of the box. It's not perfect, but it's close enough to being perfect that I've worked in summarization before, and I don't know if there's a whole lot more that we can do there. Of course, multilingual is interesting. Multi-document summarization is definitely not solved. In multi-document summarization is when you have lots of documents about a particular topic, and you want to summarize them down into a coherent summary of that topic. One example of that is Wikisum. This is a data set where you're provided with all of the links to pages about a Wikipedia article, and you're expected to generate the first paragraph or few paragraphs of the article. And so you're expected to take like lots of noisy, incoherent articles about Barack Obama and actually write about Barack Obama, something like this. Some other example interesting tasks for this include things like survey generation for papers or something like that. You want to know everything about a scientific topic, or generating a report of all the things that happened in the stock market today or something like that. There's lots of places where this could be useful. Another class of tasks is information extraction. There's lots of examples of this, but basically they all boil down to extracting some sort of information in structured format from text. And this is things like entity recognition, identifying which words are entities, entity linking, linking entities to a knowledge base, entity co-reference, finding which entities in an input correspond to each other, event recognition, linking co-reference. So all of the same things, except doing it for events instead of entities. An example data set is something called Ontonotes. It's an older data set, but it has all of these things annotated, and you can extract things from this. There's lots of other data sets for this too. Also, kind of more in general, you can think of like, what if I gave you an Excel sheet? Could you go and like fill in Excel or Google Sheet? Could you go and fill in all of the columns in the sheet appropriately, given all the information on the internet? So this is a pretty important task category as well. Translation. So I don't really need to talk that much about it. It's translating from one language to another. For both translation and summarization, evaluation is kind of tricky. I'll talk about this in the future, but basically you assess quality based on similarity to some sort of reference using things like BLUE score or neural metrics. An example of this, which I think is actually a really nice example, is something called the Flores dataset. And this is a translation of several, or like 1,000 Wikipedia, not 1,000, but like quite a few Wikipedia articles into 101 languages. The reason why I like this data set a lot is because if you could translate into all of these languages, you would be able to, aid information dissemination across the world, make access to information more equitable. So I like this data set a lot. Separately from this, there are general purpose benchmarks. These benchmarks are not really for the purpose of evaluating any specific task that people think is actually useful, but rather trying to test the language abilities of language models themselves. A typical example of this is Big Bench. And this contains a whole bunch of tasks that test, different abilities. I have some examples here. These are very small, so you might need to look at the slides to see them. But for example, this is tracking shuffled objects like Alice, Bob, and Claire are friends who occasionally trade books. At the start of the semester, each one has a new book. Then they trade, then they trade, then they trade, then they trade. Which one does Bob have? Today is Christmas Eve of 1937. What is the date tomorrow? And you need to write it in the appropriate format. Sherry tells the truth. Vernal says Sherry tells the truth. Alexis says Vernal lies. Michaela says Alexis tells the truth. Eleanor says Michaela tells the truth. Does Eleanor tell the truth? Hope you all got that one right. So like it's just these kind of exercises. And like when you look at how language models are being evaluated, they're being evaluated against like many of these tasks, not all of them necessarily, but many of them. I think Gemini evaluated with respect to all of these task categories except information extraction, maybe. So these are kind of typical task categories that people look at. Cool. Any questions about this? Nice. Okay. Yeah, sorry.
How do they ensure that
How do they ensure that similar data does not appear in the training data? So people have tried a bunch of different things. This actually might be a good thing to talk about at some point when we talk about data curation or things like this. The first thing is you actually create the data. So similar is actually okay, right? Because, you know, if it appears everywhere on the internet, GPT-4 will learn it. The problem is like if the exact same thing appears. So number one, how do we prevent this from happening? Number two, how do we even tell that it did happen? So some things that people do to tell that it did happen is they make small perturbations to the test data and test whether that like drops the model score by a whole lot. There's actually a paper, I don't know if I can find it immediately, but there was a paper recently that just like swapped the order of outputs in MMLU and saw that the accuracy went down for some language models. So that should make no difference whatsoever because you're just changing the order of answers, but it caused the outputs to go down. If that's the case, it's a pretty clear sign that it's leaking. Other things that people do are change the input a little bit. So like change the number in a math problem to be a slightly different value and see if that hurts the accuracy overall. And like making these little perturbations that shouldn't change the accuracy. And then if they do significantly, then you think there's a problem. So I think that's a basic tool to diagnose this. How do you prevent it from happening? There's really simple and silly things that you can do, like zip the file and like put a password on the file. And then like a scraper, even if it's scraping all of GitHub for training data, it won't scrape your zipped and password protected file, right? So that's kind of a first line of defense. It doesn't work if someone puts it like, you know, someone puts it somewhere in unzipped format. So that's a problem, but you know, there are things that you can do like that. Another thing you can do is just not reveal your data whatsoever. So you can keep a private version of the data. You can keep a private version of the data and not, you know, let anybody else see the outputs. So yeah, it's pretty tricky. Yeah. How do you control for task complexity? That's a great question. I don't think there's any really good definition of task complexity yet. Some things that you can do are control for like length or control for, you know, the number of hops that are required in like multi-hop reasoning. There's actually one really interesting work that tries to do not control necessarily, but at least evaluate. There's actually a couple. So what this tries to do is this tries to break down questions into kind of like operations that you would need to do to solve them. So it's like which keywords have been contained by more than 100 ACL papers, and they say, okay, first you need to select, then you need to filter, then you need to project and stuff like that. So they try to at least express the level of complexity in this way. There's also another one that's not on so much on real data. Sorry, this is called the break benchmark if you're interested. There was also a more recent one paper that I liked that tried to do something somewhat similar. Where they come up with like math or programming problems and try to express them as a graph and then do some examination of how transformer models do on things of different complexity. I think the problem is there's so many different things that could make something hard or easy. There's also like, is it in distribution or out of distribution from the point of view of topic or language or speaking style or things like that. And actually, I think we're going to talk about this in the debugging and evaluation lecture, but like one of the things I really like to do is I like to subsegment the data and look at different subsegments of the data where I think the subsegments will affect accuracy by a lot. And basically anything that you could subsegment on is like something that determines difficulties. So yeah, lots to say about that basically. Cool. Any other questions? Okay. If not, let me get on to instruction tuning. I don't have a whole lot about instruction tuning because it's conceptually pretty simple, but I would like to talk about all of it. So basic instruction tuning, was proposed almost simultaneously by people at Google and people at Hugging Face. The way it works is you have tasks and you train on lots of tasks where you append the prompt and you append the prompt, you append the input, and then you just try to train to generate the output. And so this contrasts from like base language model training because you're still training a language model based on a prompt and an output, but you're specifically formatting them in a particular way so it corresponds to solving tasks. It's essentially supervised training, but supervised training over many, many tasks, fine-tuning over many, many tasks. The interesting thing that these papers showed was that basically, if you do this instruction tuning, you do well not only on the tasks that you trained on, but also on new tasks that you didn't train on. And so this is now really like important. It's incorporated in every serious language model that's used in a kind of like production setting nowadays. And yeah, so I think that's the basic idea here. You can also do things like learn to in-context learn. So we talked about in-context learning. So in-context learning, instead of giving just a prompt, you give training examples in the context. And so that's what you do in this paper here as well. You sample a whole bunch of training examples, you append them to the context, and then you train the model. And so why is this good? This is good because it will train a model that's better at in-context learning, basically. So if you want to provide these training examples, then you can train it like that. So these are the two basic ways of doing instruction tuning. All came out around the same time. There are a bunch of data sets that people have compiled. And you probably, if you want to do any sort of instruction tuning, you probably want to use one of these data sets because compiling together a bunch of data sets is just annoying. It's not hard, but it's annoying. And so I very highly recommend this paper on the FLAN collection because it gives a good summary. It has this really nice table that breaks them down based on like, what's the name of the data set? What is the size of the training data? What prompts do they use? Zero shot or few shot? So like few shot is learning to in context learn, like I mentioned before. How many tasks are there? And what detailed methods do they use? So you can take a look at this. Some very popular ones that lots of people use are things like the FLAN collection from here. Also, natural instructions is a very popular one that still people use a lot. And self-instruct is a popular one that I'll talk about in a second. Cool. So the second thing that I want to talk about is instruction-tuned models, or the next thing that I want to talk about is instruction-tuned models. These are examples of models that like I can recommend you use now in 2024. They're like good models to use. FLAN T5, I think, is a very good model, especially it's a very good model for its size. And it comes in various sizes from smaller models to those up to 11 billion parameters. And it's an encoder-decoder model based on T5 that was trained on lots of data. My impression is that this is a model that's like consistently good at anything that's like a simple input-output style task, not like a chat task. So if you just have input-output, you want to do like Code generation, you want to do, maybe not code generation. You want to do like summarization or other things like that. That's a good model to use. Another one is Llama 2 Chat. So Llama 2 Chat was instruction tuned and kind of tuned with human preferences, but it is quite good at following instructions. And then there's also, excuse me, Mixtral Instruct. And these are both decoder only models. Mixtral is a decoder only mixture of experts model. Mixtral is smaller and quite strong, so I would recommend that you consider this maybe as a default if you want a decoder only model, and then Flan T5 if you want an encoder decoder model. Cool. The final thing I'd like to talk about a little bit, and then we're also going to talk about it a bit more in the distillation class, is dataset generation. So it's possible to automatically generate instruction tuning datasets. And the first or typical example of this is self-instruct. And the way self-instruct works is you have a bunch of seed tasks that have one instruction and one instance per task. You throw them into the task pool. And then based on this, you do prompting to try to generate new tasks, basically. And you identify what type of task it is. And then based on the task, you generate inputs and outputs. And from these inputs and outputs, they do a little bit of minimal filtering to deduplicate the data set and also remove things that require like visual information and other stuff like that, and then feed that back into the task pool. So basically, like they start with 175 examples, and then they expand this data set to be very large, cover many, many different tasks. This is pretty influential. And like one interesting thing that they showed here is that you can improve the model that was used to generate these itself. So basically, they took this and they used it to fine-tune GPT-3, basically. They used GPT-3 to generate the tasks, and they used it to fine-tune GPT. Some other more recent examples are chain of thought, tuning for chain of thought. So Orca is a nice example of this. This is something where they generated explanations for why the model made a particular decision, and then they use that to train models and improve their essentially reasoning capabilities. Another interesting example is something called eval instruct. And basically the idea here is they start out with a seed set of instructions from any data set that you want to be using. And they modify those instructions to make them more complex. So they say, okay, this is too easy. Let's make this harder. And that makes it possible to improve the ability of models to solve complex problems. So this is actually a really popular, area overall nowadays. I'm not going to do it justice in one slide, so we'll talk a bit more about it later. But this is the general idea. Oops. Cool. And yeah, that's all I have for today. Any questions? Or, yeah.
When you contrasted instruction tuning with tuning, can you talk about other cases where you want to do
Oh yeah. Sorry. Very, very good question. And I actually wanted to put that on my slide, but I just realized I forgot. So thank you for prompting me. So when would you want to do single task fine tuning versus instruction tuning? If you have a very if you have a very clear task definition and you have lots of training data, doing full fine tuning can be good for a number of reasons. Number one, you can get maybe slightly superior accuracy with bigger models, but you can get much superior accuracy with smaller models because smaller models don't have the capacity to do really, really well on lots of different tasks. So I think you'll see, some improvement, maybe a somewhat marginal improvement on bigger models, but you'll see a big improvement on smaller models. And there have been some interesting results on this recently. Like there's a really strong text to SQL model that was based on Llama 7B that was just trained on tons and tons of text to SQL data, for example. And so there's certain tasks where it's really important. Another example is on translation tasks, there's a model called NLP, which is 3.3 billion parameters. And it's competitive with GPT-4 on very large languages with lots of training data, and way better than GPT-4 on languages with less training data. So it just shows how, like, if you very carefully work on a special purpose model, even if it's very small compared to the bigger model, you can still do a really good job. So I think that's the biggest use case. Another thing is if you have a very fixed format and you always want something in a format, you might want to be doing that.
Yeah, in the previous page, since you are only into one instruction into generation, instruction generation modes, try to help with that different types of generation.
Well, you are inputting at least 175 seed ones, and you're sampling from the model, you're asking it to generate new instructions. So if you have a model that's good enough at following instructions, it'll be able to generate something new.
So in your free text, there will be user output
for this. Yeah, they have a class. I believe they have a classifier that says it will be one of these two.
Yeah, I mean, when you're including the free text are like it can be both interface the output.
Mm-hmm. Yeah. Well, but also the seed test can be input first and output first, and you're like generating a new instruction from the LM. Here. So this is from the task pool, but you're asking the LM to generate a new instruction. Yeah. Cool. Anything else? Okay. Yeah, that's all we have for today. So thank you.